Morning, welcome back. We are going to start talking about some thermodynamics. I wanted to go through a little bit today as far as some housekeeping for the class, just because it's our first meeting after spring break. So one of the big things is grades coming up. At the end of the week, I'm going to start submitting grades. Right now, they're as up to date. There might be a couple test corrections that are still getting in, but for the most part, everyone's earning credit in the class. You're getting either credit or no credit. And since we don't have any Fs right now, then everyone gets credit for quarter three. So I'm pretty happy with that. And then as far as quarter four goes, we're gonna still be doing assignments and be turning in work, and you'll be earning credit or no credit. And that's just to account for the wide range of accessibility issues that people might have while we're learning from home. So I do not know how that affects GPA or any of that kind of stuff. I'm sure that information is gonna be coming out in more detail. We just are getting information about just how we're going to be grading. So it's still very early on. And if it does change, then I'll make sure to update you as well. When we were in class, we finished up talking about solutions and mixtures and a little bit with temperature changes and phase changes. So thermodynamics builds upon that. And we're going to be studying the heat transfer between objects. And just because you have experience living in this world, you've experienced differences in temperature, differences in heat. But from a chemistry point of view, it gets a little bit more in detail as far as how are we actually measuring heat? What is temperature versus heat? And so we'll get into those discussions throughout the week and next week. You do have assignments on Google Classroom in the classwork section. The assignments are going to be usually due on Friday, so you have all week to work on it. I'm not taking attendance during these meetings. You can watch them from YouTube later. Just make sure that the week's worth of assignments that you are submitting them by Friday. The next assignment I'll assign is going to go up on Google Classroom. Usually I stop assigning work on Wednesday. So you have the last assignment for the week on Wednesday, and you have Thursday, Friday to finish it and turn it in. Any questions on that? You can go and type in chat or unmute yourself. I'm going to pause the video really quick. All right, so we're going to go ahead and get started. Thermodynamics. So thermo is a word for heat, every word for heat, and thermodynamics is one form of energy. There's a lot of different forms of energy, and so a follow-up conversation we're going to have in a later meeting is the different types of energy. The first assignment I'm going to give you starting today is going to be a little worksheet to help you explore the different types of energy. But thermodynamics specifically focuses on just heat. So when we're looking at chemical processes, whether they're physical or chemical, physical being like phase changes or temperature changes, chemical being actually chemical reactions, there's usually heat transferred in the process. Just the idea of measuring temperature is a way of measuring how much heat a substance has absorbed or released. If the temperature is increasing, that's a result of an increase in heat energy of the system. And often that heat energy goes into kinetic energy, where the particles are moving faster or vibrating faster, which is common for solids. Solids still have kinetic energy. They're more in vibrations than actual motion. So when a process happens and there's energy change, whether it's absorbed or released, if we write a chemical reaction for it, we can say that it's a product-favored reaction. If the reaction generally proceeds spontaneously and energy is released in the process. When it's a reactant-favored reaction, usually that's where energy is required for the process to occur. Like when you're melting ice, the ice needs to actually absorb the energy in order to melt. So we'll be using these ideas of product-favored and reactant-favored reaction a little bit later when we get into chemical reactions. One of the big concepts that drives this is the law of conservation of energy. Energy can be converted from one form to another, but it's neither created nor destroyed. So it's really easy to see with conservation of mass that all mass is conserved in a reaction, but now we're going to be saying that energy is conserved. Energy just doesn't disappear, it changes form. So for example, when light photons enter a system, that light can be transferred into heat energy. That's why your body feels warmer when you're out in the sun, because the photons from the sun travel at the speed of light, and once they hit your body takes that energy and converts it to heat, and you feel warm. So the two main types of energy that you're going to commonly hear in a science classroom is kinetic energy and potential energy. And from, hold on a second. Okay. Some ways that we measure energy is window is not. Okay. So there's a couple different ways we can measure energy. Calorie is the most common, and you're hearing this when you are eating food. It's usually the unit of energy for food. And the calorie defined in a chemistry classroom is actually the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So when you're eating food, that food is converted to energy, and your body uses that for a variety of processes. We're just using water as a standard for measurement as far as what a calorie actually represents. So when you're heating up water, the burner is providing energy to the water, and based on how much water you have in the pot and what the temperature is, how the temperature is changing, we can measure the calories that is absorbed by the water, transferred from the heat source to the water. So we're going to be talking a lot about transfer of energy from one source to another. Calories, one way we use it, we often use joules actually, because joules is more the international scientific measurement. Calories more for food, joules is more for chemical reactions and heat change. When you look at the nutrition items on a cereal box, for example, or you're going and you see the calorie counts in a restaurant, those calories are actually 10,000 times more than what they're presented. So you go and eat a burger, and the burger is like 400 calories. It's actually, in science, it's actually 400,000 calories, because a nutritional calorie is 1,000 times more than just a regular calorie. They're not going to put 400,000 calories on a menu, so they reduce it by a factor of 1,000. So some things that food represents in terms of calories: 5 pounds of spaghetti actually has enough energy to brew an entire pot of coffee. Piece of cheesecake can power a light bulb for an hour and a half, and over 200 Big Macs could actually drive a car almost 90 miles in terms of straight energy conversion. Obviously, we're not at the point where we're feeding cars burgers, but interesting thought. So we're learning a little bit of terminology today, and when we're talking about heat transfer, it's important to reference where the heat is flowing. So we often use the word system and surroundings to discuss transfer of heat. If heat is, let's say you step outside and you are, it's on a cold day, you're referencing yourself as the system, and the air around you is the surroundings. So when you feel cold, that's actually heat leaving your body, you the system, and transferring it to the surroundings around you. And the term universe just includes system and surrounding. We don't use the word universe a whole lot, but mainly just system, the idea of system and surrounding. In a lab experiment where we're actually using chemicals, the chemicals and the containers can be the system. So all the reactions contained inside the system, and then the surroundings is the area around the beaker. So when we're trying to do heat transfer reactions, we often try and contain everything inside the system and avoid any sort of heat leaving the system and entering the surroundings. It's like an insulated cup. So when you're taking coffee with you, bring it in an insulated cup, that keeps all the heat inside and avoid it from leaving and transferring to the surroundings. The word exothermic, exo means outward or external. In biology, I believe you use the word exogonic. I'm not sure if you use exogonic in regular bio that much. But an exothermic means heat transferring from a system to the surroundings, heat leaving the system. And exothermic is commonly referred to or attached to reactions where they're releasing a lot of heat. So when we did the gummy bear experiment where we set the gummy bear in the molten potassium chlorate, the gummy bear jumped around and released a ton of energy. That was an exothermic transfer of energy. And the other word that we're going to use is endothermic. Endothermic is where when the reaction proceeds, it actually requires some energy, needs to absorb some energy for the reaction to happen. So either energy being released, exothermic, or energy being absorbed, endothermic. So just being able to assess the situation and understand what the heat's doing, where it's transferring, whether it's inward or outward, we just attach these words to it as well. An example of a chemical reaction. Sometimes you'll see heat or energy written in the chemical reaction. So for endothermic, the heat would be written on the left side of the equation. And for exothermic, the heat would be a product on the right side of the equation. And if you have a question and you don't want to jump in on voice, you can always just type it out. I'm checking chat regularly. So this is where we're going to be talking about heat transfer. Heat will naturally travel from hot to cold. So let's say, here's you. Maybe you have long hair. Maybe you have glasses. And you're treated as the system, and you are around 98 degrees Celsius, or Fahrenheit, excuse me. And then outside, it's a nice brisk day. I think it's around 65 Celsius or 65 degrees Fahrenheit outside. You are considered the hot source because you're at a higher temperature, and the air around you is considered the cold source. And so heat naturally, it's just physics, naturally is going to flow from a hot source to a cold source. And that process will actually happen until they reach the same temperature. So your body is constantly trying to heat the air up around you to reach about the same temperature, to reach which is called equilibrium. Now, obviously, it's not going to happen because the air keeps recycling around you. But it's just this natural tendency of heat flow that we experience and we observe. During phase changes, energy is absorbed or released. It's not changing the temperature during phase changes, but it is used to rearrange the position of the molecules, whether they're moving further away from each other, moving faster, or getting closer together and more stationary. We've seen a graph like this when we were looking at phase changes, and the phase changes in particular happen at the part where it's red. And you can see that there's no temperature change where the phase changes are occurring, but the energy is still being absorbed. In this case where we're going from left to right, temperature is increasing, energy is being absorbed. It doesn't necessarily change the temperature. It can also go to change the position of the particles from solid to liquid to gas as well. And that builds upon what we learned from phase changes last chapter. This is a fun little comic that I picked up years ago. Instead of letting the cold air in, you're letting the heat out. It's just a change of perspective. Hold on, my dog's going crazy. Sure. All right, I unlocked it. So we can use this idea of heat transfer as from flowing to hot to cold to help us describe why ice melts when you put it in hot water or tea. If I'm going to draw out this example. We have a little cup, and we've got the hot water in there, and we stick an ice cube in there. We should be able to describe what is happening to the energy between the hot water and the ice cube. So in terms of just heat flow, it's not necessarily that the ice is cooling down the water. It's more so that the hot water is heating up the ice. And it's just a change of perspective when we're talking about heat flow in chemistry, just thinking of where the heat is going, which direction. And once ice reaches a certain temperature, the hot water transfers its energy into the ice cube, and allowing the ice to melt. That transfer of energy does result in a loss in temperature of the hot water. So the temp of the hot water goes down as it transfers energy into the ice cube. I unlocked the meeting. Okay. Now I locked it again. All right. And so an answer that I prepared is to undergo phase change, the ice from solid ice to liquid water, energy is required. So the ice is going to absorb that energy from the hot water. Just being able to describe heat flow for certain examples like ice and warm liquid, be able to talk about it in a chemistry point of view where heat is transferring. And to attach the term that we introduced earlier, this would describe an endothermic process where the ice has to absorb energy. Okay. Same thing when you brew a cup of coffee or you have hot tea and you just let it sit on the desk, eventually the tea or the coffee is going to cool down. And it's just the natural flow of heat with the surroundings. The heat is leaving the cup and joining the air around it, from system to surroundings, from the cup to the air around it, just providing some perspective. Now, we can talk about the flow of heat, but in chemistry, we often do some calculations to predict exact values or close to exact values of how much energy is actually being absorbed or released in the process. So the first thing I want to talk about is specific heat. Specific heat is the amount of heat required to raise the temperature of a substance, 1 gram of a substance, by 1 degree Celsius. So when we're talking about water and heating up water, we actually have a specific heat value for water that describes how much energy the water needs to absorb to increase the temperature of that substance. And each substance has a different, unique, specific heat value. If you look in the book, chapter 17, it actually has some tables of specific heat values for common substances. Water has one of the highest specific heat values. It actually can absorb a lot of energy. That's why water is used very commonly to be a heat sink. When you're running nuclear power plants are built near water sources, so it can pipe water into the power plant and use it as a cooling mechanism. It's one of the best things that we have to absorb heat and help cool down substances. Also being a natural resource helps. So usually the specific heat is a value that I would provide to you. It would be given in the question, and we just use it in some of our calculation. Now, specific heat is based on a couple factors. Specific heat is based on the mass. The more you have of a substance, the longer it's going to take to heat up. When you have a pan of water, filling it up with how much water is significant. If you're just cooking top ramen, you're not going to put a whole lot of water in it. But if you're cooking a big pot of pasta, you need more water. It's just that the more water takes longer to heat up. So mass is one important factor in specific heat. How much stuff you have, more of it is going to take longer to heat up. So which will absorb heat faster? 25 mils of water or 3 liters of water. Less water will absorb that energy faster in terms of when we'll be able to measure that with temperature. So the temperature will change faster for the smaller source of water. One of the key equations we're going to use is just like an algebra equation that we're going to plug numbers into to do some calculations, is Q equals MC delta T. Q is a letter that is used to measure heat. So when we're calculating Q, that's the heat energy, whether it's absorbed or released by the source, the substance. C is the specific heat value that's unique for a particular substance. So for example, the C value for water is 4.2 roughly joules per gram degree Celsius, where the C value for aluminum metal is less than 1. I think it's about 0.7-ish. I got to check the sig figs on that. But we can see a large difference in a C value for water versus aluminum. This suggests that aluminum changes temperature much faster than water does because it requires less energy per degree to change temperature. If you ever notice you have aluminum foil in the oven and you're cooking something on there, you take it out, you can touch the aluminum foil pretty quick and it's not going to burn you. Mass is a factor, so M is a component in the equation, and the change in temperature. So basically what we're doing is we're taking a substance and we know its mass. Let's say we have a 10-gram substance, and we're going to measure the temperature change over a period of time. So the temperature goes from, let's say, 5 degrees Celsius all the way up to 30 degrees Celsius. Well, how much did the temperature change? What is the mass of the object? And then based on the specific heat of the object, these three factors, we're able to calculate how much heat was actually absorbed in the process. And so we're going to run through a practice calculation. We're not going to do a whole lot of these past with this kind of, the Q equals MC delta T equation. We're going to use this in calorimetry to determine how much heat is transferred between two objects. So this is really the only calculations we'll be doing in this section. The sign, whether it's positive or negative, is important when we're talking about heat transfer. An exothermic process is actually going to have a negative value for Q when you plug in your mass, your specific heat value, your temperature. And then your end result for Q will be positive when it's an endothermic process. Remember, exothermic is going to be a release of energy or a loss of energy by the system because it's giving away to the surroundings. And then endothermic is going to be absorption of energy. So the system is going to gain energy, it's going to take it in, which is a positive value mathematically. So just having an association with positive and negative is going to be helpful as well. So I'll run through a sample calculation and we'll see how this goes. So how much heat is absorbed by a 100-gram cup of water if its temperature increases from 20 to 35 degrees Celsius? How much heat did it take in from an outside source? So often we're talking about transfer of energy or some sort of process. I like to draw a diagram. So let's go back to our cup. And we're going to do before and after. So nothing too fancy, but we have 100 grams and the mass is staying the same. So we have a 100-gram cup of water and it's just going from 20 degrees Celsius to 35 degrees Celsius. And we're trying to determine how much energy was gained in this process. So another way to do this is we're going to assign variables to the equation Q equals MC delta T. We're going to solve for Q. So let's assign values. Mass is going to be 100 grams. The C value for water was given. And these are usually book values on a table that you'll be provided. We just have to know how to do it or how to use it. This is 4.2. And if we notice the units on this are a little funky, joules per grams degrees Celsius. And this is just used to unify the equation. It's a connecting value to connect mass and temperature with heat. The capital J is joules, and that's the units for heat, energy. And then the delta T is a little tricky if you haven't had too much experience working with deltas in math. Delta T is actually a change. That's what the delta represents. Delta is change in temperature. And anytime you do a change in a value, you're going to be subtracting the difference in temperature. You're going to take the temperature of the final value, the final state, minus the temperature of the initial state. And so you can substitute this into delta T anytime you see the delta. In this case, we're going from 20 to 35. So the 20 is going to be the T initial, which I'm going to label as TI. And the 35 is going to be the final temperature, which I'm going to label as TF. So to get the delta T, it's going to be 35 minus 20, which is a positive 15. And the positive is going to be important to recognize. In this case, it's Celsius, so we'll put degrees Celsius. The sign of the delta T is going to help us to determine the sign of Q. If everything is positive, Q should pop out as positive. So I have 100 grams, 4.2, and 15, and I'm going to be plugging these into the equation. So I'm going to go and clear this out. Q equals MC delta T, and I'm going to substitute on my next line. We have 100 grams. C is 4.2, our given value for water. Pure water will always have a value of around 4.2. It's a rounded number. And then for delta T, I'm going to do 35 minus 20 for the T final minus T initial, which is how we solve for delta T. The delta thing you've done before in math, when you do graphing, you have slope, the change in y over the change in x, and you're actually, so delta y over delta x for slope is actually y minus y, like y2 minus y1, x2 minus x1. You've actually done this delta y calculation before by subtracting. Same idea. We're just doing it with temperature. And so what we're doing is we'll just plug this into our calculator. I have my high-tech calculator phone app. And I'll just plug these in. So 100 times 4.2 and then times 15. So this value gets pretty large, 6,300 joules. You can see the grams canceling out. And for temperature, temperature is degrees Celsius, so the degrees Celsius is also going to cancel out. And we're left with just joules. And joules is our unit of energy. Now, 6,300 joules sounds like a lot, but actually, we often deal with energy in kilojoules. And it's just 6.3 kilojoules. To convert from joules to kilojoules, there's 1,000 joules in 1 kilojoule. And so it's just a matter of moving the decimal 3 decimal places. And so if the answer asks you to express it in kilojoules, you'll have to convert it to kilojoules by moving the decimal 3 places. There we go. And as we do more practice and see more examples, we'll start seeing a reference of what 6 kilojoules actually represents, what you're able to do with 6 kilojoules. But for now, we're just practicing using this equation and connecting mass to specific heat to a change in temperature. So as far as assignments and when you're going to see this, you're not going to see this on the assignment I'm giving you today. This is just a little exposure. You can see it in the textbook. There's even in 17.1, chapter 17.1, they start doing some calculations like this. But I'm going to work up to this as far as you doing it on your own. We'll get some more practice on our next meeting using these type of calculations and get a little more context. So that's it for now. If you're in the meeting, you want to stick around and ask questions about the class or this lesson in general, go for it. I'm going to post our next assignment and I'll show you in the Zoom meeting what that's looking like, and then that'll be submitted through Google Classroom. Thanks for joining, and I'm going to go ahead and stop the video.